Hello, everyone. My name is Dongden. I'm from Rutgers University. Today, I'm going to present our work on near-duplicate text alignment. Let's get started. Textual data is ubiquitous. It takes account for about 18% of all information. And many widely used applications, such as Twitter, Wikipedia, Reddit, and news articles, generates enormous amount of textual data every day. On the other hand, textual data is usually very messy. It contains a lot of typos, abbreviations, synonyms, etc. It is also estimated that about 14% of all web contents are near duplicates. In this paper, we're interested in the near duplicate text alignment problem. It takes two long texts and a Jacquard similarity threshold as input. And it produced all the passenger pairs in the two long texts whose Jacquard similarity is above the threshold. Maybe the most typical application of this problem is plagiarism detection. For example, in academia, reusing a passenger in another paper without quotation is deemed as plagiarism. Here on the slide, we show the two speeches addressed by two first ladies in the United States. And the highlight parts are an example of near duplicate passenger pairs. The challenge of this problem is the high computation cost. This is because for text with n words, it contains n square passengers. And for a pair of long texts, there are way too many passenger pairs in them. For example, for a pair of academic papers with tens of thousands of words, they have quintillions of passenger pairs. And it would take a normal CPU more than 13 years of calculation to just enumerate all of them. Existing approaches typically use some heuristic rules, and the most frequent used one is seeding, extension, and filtering. In the seeding phase, a lot of exact matches of short passengers are first identified as seed matches, and the seed matches are extended on the two ends to form candidates. And finally, the candidates are filtered and verified to generate the final near duplicate passenger pairs. In the PAN 14 plagiarism detection competition, the champion method adopted this seeding, extension, and filtering heuristic, as well as a bunch of other heuristic rules. And it involves more than 10 hyperparameters, which is hard to tune. Another category of related work is fingerprint-based methods. For example, Winnow in Sigmod 2003. And this fingerprint-based method works only for exact duplicate passenger pairs, and it can also be used to find seed matches in seeding, extension, and filtering. In this paper, we propose a min hash-based method. In min hash, every word in a passenger is converted to an integer. And the min hash of the passenger is the minimum word hash value in this passenger. And if we do multiple hashes, the ratio of common min hash in two passengers is an accurate and unbiased estimator of their real Jacquard similarity. However, there are still quadratical min hash in a text. We observe that a lot of nearby and overlapping passengers would have the same min hash value. For example, on the slide, the four passengers, T57, T49, T27, and T48, they all have the same min hash value 20. Based on this observation, we define a company window using a tuple of 5 elements, where T is the text, F is the hash function, L, R, C are 3 integers, where L and R are the left and the right boundaries of the company window. And C is the index of the word with the minimum hash value in the company window. We also call the sixth word the pivot word of the company window. And the company window satisfies maximal boundary. That means we cannot extend the boundary by one more word. Otherwise, we would introduce a word with smaller hash value than the pivot word. Here on the slide, we show two example compact windows. On the left, the compact window TF1296 is a compact window from the second word to the ninth word, and it has a mean hash value of 20. And as we can see on the slide, the first word and the 10th word both have a smaller hash value than 20. Thus, we cannot extend the left or the right boundary by one more word. Clearly, based on the definition, all the passengers TIZ, where I is between L and C, and J is between C and R, would have the same mean hash value, which is the mean hash of the compact window. To generate the compact window, we can scan all the position in a text. And for each position C in the text, we use it as the pivot word, and we extend it on the two ends as far as possible until we met the first word with a smaller hash value than the pivot word. Based on this process, we can see that there is one and only one compact window for each position C, assuming that there are no duplicate words in the text. We will discuss how to deal with duplicate words later. And in total, there are only n compact windows for text with n words. Furthermore, we can prove each passenger is in one and only one compact window. To see this, on the one hand, for each passenger TIZ, assume C is the index of the word with the minimum hash value in the passenger TIZ, and this passenger must be in the compact window with pivot C. On the other hand, assume this passenger TIZ is in two compact windows with two different pivot words, C1 and C2. Based on the definition of compact window, C1 and C2 must both have the smallest hash value in the passenger TIZ, which contradicts with each other because we assume there's no duplicate word in the text. Based on this discussion, we can see that all the quadratic number of passengers in a text can be represented by the linear number of compact windows in the text. The previous scanning-based method has a quadratic time complexity, which is very expensive for long text. To address this issue, we propose a divide and conquer-based method. In this method, it takes an interval L and R as input, and it finds the word TC in the interval with the minimum hash value. And then it generates a compact window using the word TC as the pivot word and the interval as the range of the compact window. Next, it divides the interval to two sub-intervals, and it repeats the above process on the two sub-intervals. As we can see on the slide, the two pivot words on the two sub-intervals must have larger hash value than the previous pivot word. That's why we can use C-1 and C+1 as the right and the left boundaries of the two compact windows of the two sub-intervals. We can use a segment tree to find the word with the minimum hash value in a range, and it takes log n time, and in total, we have n intervals. Thus, the total time complexity decreases to n log n. Once we find the compact window for two long texts, we pair the compact windows in the two texts with the same mean hash. For example, here on the slide, we show two compact windows with the same mean hash, which is the hash value of the pivot words. Clearly, all the passenger pairs in the compact window pair must share the same mean hash. And we pair all the compact windows for each hash function. And next, as shown on the slide, let the shadow part be the intersections of the compact window pairs. And here we can tell that all the passengers starting and ending both in the shadow paths must share 3 common min hash. This is because all the passenger pairs must appear in these collided compact windows. Once we find all the compact windows, once we find all the compact windows for 2 taxes, we pair their compact windows with the same min hash. For example, on the slide, we show 2 compact windows from the 2 texts T and S with the same min hash, which is the hash value of the keyword words. And we can tell that all the passenger pairs in this compact window pair must share the same min hash. And we do the same for every hash functions. Here, as shown on the slide, that the shadow part be the intersections of 3 compact window pairs. And we can say that all the passenger pairs starting from the shadow parts and ending at the shadow parts must share 3 common min hash. This is because all these passengers are within the 3 compact window pairs, and each of them has 1 common min hash. Thus, our problems becomes find all the subsets of compact window pairs whose intersections are non-empty and whose size is at least k times theta. We can also support a few practical constraints. For example, we can support the sentence level near duplicate passenger pairs. That means we only report near duplicate passenger pairs starts and ends with periods. To support this, we can enforce that our compact windows start and end with periods. Furthermore, we can support a length threshold T such that we only report near duplicate passenger pairs whose length is at least T. And to support this, we just need to enforce the compact window size to be at least T. And the last, we can also support the longest near duplicate passenger pairs. That is to say, if there is a near duplicate passenger pair covered by a longer near duplicate passenger pairs, then we won't report it. We can support this using length dominance. Please see more details in our paper. Finally, to support duplicated words, we just need to adapt the definition of compact window a little bit. Specifically, we add another integer, LE, in the tuple of the compact window. And now the compact window represents all the passengers, Tiz, where I is between L and LE, and the J is between C and R. And furthermore, all these passengers would have the same min hash, which is the hash value of the keyword word TC. But notice that since TC might appear multiple times and each time it has a different hash value, we further require that in all these passengers, TC has the same multiplicity, let's say X. Or in another word, the word TC appears exactly X times in the range from LE to C. On the slide, we show an example multiplicity compact window, TF1 11313. It represents all the passengers T13, T14, T15 till T113. And on the slide, the word U appeared 3 times. And in a window, if U appeared first time, it has a hash value of 18.4. And for the second time, it has a hash value of 10. And the third time has a hash value of 39. And as you can see, all these passengers in this compact window, their min hash is exactly the hash value of the keyword word T3, which appears the second time in all these passengers and has a mean hash of 10. In the experiments, we used the PAN14 plagiarism detection competition dataset. It contains a lot of manually paraphrased passengers. And even for the champion method, it has a low recall. We run all of our experiments on a Ubuntu server and implement all the methods in C++. In our method, we have 3 hyperparameters, where k is the number of hash functions in min hash, theta is the Jakarta-Similarity threshold, and t is the length threshold. And we compared with 3 baselines. The first one, pk-wise, which generates only fixed lengths near duplicate passenger pairs. And SEF, short for seeding, extension, and filtering, is the champion method in the PAN14 competition. And it has more than 10 hyperparameters, which is hard to tune. The enum method is the brute force method. And here is the experimental results. We first evaluate the accuracy of different methods on plagiarism detection task. And as you can see on the slides, the method pk-wise has an extremely low F1 score. This is because it only reports near duplicate passenger pairs with fixed lengths. And the SEF, which is the state of the art, has a low recall, just the 0.42. And our method, Allign, improved the recall of SEF from 0.42 to 0.48. And furthermore, if we combine the 2 methods together, we can further boost the F1 score to 0.51 while achieving similar precision score. Next, we compared the efficiency of our method with the baseline method and the brute force method. Since the baseline method and the brute force method are very inefficient for long texts, we only used a pair of texts with tens of sentences or hundreds of words in this experiment. And even for this not so long texts, the brute force method and the baseline method, pk-wise, both took hundreds of seconds. In contrast, our method, Allign, only took 2 to 3 seconds. And the enum is a brute force method that generates all the passenger pairs whose Jakarta similarity is above the threshold, while our method, which is based on min hash, is an approximate method. But nevertheless, Allign still achieved like a very high precision and recall close to 1, even for a small k of 100. Finally, we report the scalability of our method. And on the left, we show the compact window generation time, and on the right, we show the result generation time. And on the axis is the length of one text, and different legends shows the text length of another text. And we report the elapsed time. For example, on the left, when one text has 10K words and another text has 100, 1K, 10K words, the window generation time goes from less than 1 second, a few seconds, to around 10 or 20 seconds. And on the other hand, for the result generation time, it goes from 0.1 second to 0.1 second to like a little bit less than 1 second. So the scalability is quite well with the text length. In conclusion, we proposed the first non-trivial method for all pair near duplicate text alignment problem. And we also developed a few novel techniques based on our novel definition of compact windows. And our technique can support several practical constraints, including the sentence level constraint, the longest constraint, and the length threshold. And finally, in the experiments, our approach significantly improved the recall of plagiarism detection. Thank you.